Hi, my name is Charles Joseph. I'm a student at CUNY SPS. This is to present the work done in my research project as part of the Data 698 course. The title of my project is Heartbeat Classification Using Deep Neural Network. So this is the agenda of this presentation. We will start off with the problem statement and objectives. Then we will move on to the data collection and analysis, methodology and approaches, results, challenges, and finally future studies and improvement. Let's move on to the problem statement and objectives. Arrhythmia, it's a heart rhythm disorder caused by certain problem in the electrical system of the heart. It refers to an abnormal heart rate or any change from your normal heartbeat pattern. How is the heartbeat diagnosed? It is through the electrocardiogram or ECG. The cardiologist or the medical practitioner manually look at the ECG signals and analyze the pattern or variations in the ECG data and annotate their observations. This involves a lot of manual effort and often find it difficult to categorize the condition based on the various pattern or morphologies in the signal. Therefore, a more accurate or a low-cost diagnosis of arrhythmia heartbeat is desirable. In this project, we will look at some of the ways to classify the heartbeat using AI techniques. We will start with the statistical way of modeling, and then we will look at especially um, the deep neural network techniques to classify the heartbeat rhythms. Moving on, these are the project objectives. Um, First, we will build a baseline nonlinear classification model using machine learning algorithms like kernel SPM. And then we will study the heartbeats of various arrhythmia conditions and devise a novel way to predict the heartbeat using deep learning techniques. Unlike the traditional way of modeling, the literature review suggested that there is a need of extracting spatiotemporal features while looking at the data and the ECG data to predict the heartbeat types more precisely. Um, Convolutional neural network, which is CNN, is more effective in extracting spatial features, and LSTM is a kind of recurrent neural network that captures the temporal features. It's primarily used for the time series kind of data. Finally, we will evaluate and compare the performance of the model with the help of confusion metrics and some of the performance metrics like precision, recall, and F1 score will be evaluated. Let's dive into the data collection and analysis. For this study, I've collected the data from a research database which was created by Chapman University and Shossing People's Hospital. The dataset comprises of 12 lead ECG data of around 10,646 patients with a sampling frequency of 500 Hz, and it labeled around 10 common rhythms for various arrhythmia conditions. For each subject, a sample size of 10 seconds of ECG data is available for use. The raw ECG was curated to remove noises from the signal, and a denoised version of ECG is available for the use. Moving on, before getting into the data, let's look at how the ECG signals are recorded. As we know, the heart works through electrical conduction, and the electrical activity is recorded by ECG electrodes placed on different places around the chest and limbs. The diagram in the right shows different parts, different places where we keep place the electrode, to record the electrical conduction. There are two kinds of electrodes. We have limb electrodes and the chest electrodes. There are four limb electrodes which are placed on two arms and two legs, and it generates basically six electric conduction data from various angles. It has two sets, primary leads and augmented leads. The primary leads are lead 1, lead 2, and lead 3. For example, lead 1 records the electrical conduction um, from right to left, and the augmented leads are derived from the primary leads, um, which are a combination of all three leads. For example, AVF is derived from by summing the lead 1 and lead 2 against the lead 3. As you can see AVF is derived from the sum of lead 1 and lead 2 and against the lead 3. The chest electrodes, there are basically six chest electrodes, as you can see. Um, it generates six electrical conduction data around the chest. That's called V1, V2 up to V6. Let's look at the characteristics of ECG signal. So the heartbeat is represented as a PQRST wave that consists of different segments such as P wave, QRS wave, and T wave. As you see here in the picture of heart, there are two uh, chambers. So there is a lower chamber and upper chamber. The lower chamber is called the ventricular wave, ventricular chamber, and the upper part is the atrial chamber. And the lower wall, there is a lower wall here that's called the myocardium wall. When a beat starts, the electric conduction happens from the top, and the atrial contraction happen, and then a ventricular contraction happen, and a ventricular repolarization happens. So I will show you a animation so that you can understand it better. Um, as you can see, the atrial contraction happens first, and the ventricular contraction happens, and the ventricular repolarization happens. The ventricular repolarization is basically returning to the original state. Okay, and it can be represented as PQRST wave. The P wave denotes the atrial contraction, and QRS complex is basically the ventricular contraction, and T wave is actually the ventricular repolarization. And these are some of the characteristics uh, uh, explanation for these segments. Okay, and the characteristics are there are some characteristics which can be derived in terms of duration, interval, and the axis of electrical conduction that we will see in some of the examples in the data in the coming slides. So, so we will focus on the data set. Um, as you can see, the data has two parts. The first part is a diagnostic data set, which primarily consists of the characteristics of the ECG signal. Um, for example, the ventricular rate is one of such characteristics. Um, that means the number of times the ventricular chamber of heart contracts per minute. Atrial rate is the same, again, the number of times the atrial chamber of the heart contracts per minute. The QRS duration is the duration of the QRS complex, time taken for the ventricular contraction. QT interval is the interval between the QT wave, um, T axis and R axis. The angle of directions of the electric conduction happens. The QRS count is the number of QRS occurrence per minute. So this is the diagnostic data set, and you can see a sample of the data set here, wherein you can see the first column is the file name. This the basically the row the row represent a patient's data. The first column is the file name. The file name consists of the raw ECG data of that particular patient, and the second column is the rhythm, which is primarily our target variable. It's a type of the rhythm. Beat is a subcondition a column which we are not using it in our research studies. And there are some attributes of patients like patient age, gender, and these are the ECG characteristics. Okay, moving on, the second part of the dataset is the 12 lead denoised dataset, which is primarily a multivariant time series data of the electric conduction from the 12 leads. So from the first diagnostic data set, you have the file name. That file name consists of the raw ECG data for 10 seconds. The sampling frequency is 500 hertz. That means 500 readings will be taken per second. That means for 10 seconds you will have around 5,000 readings. So basically this 12 lead denoised dataset has a dimension of 12 into 5,000. That means we have 12 columns and 5,000 rows. Moving on, these are some of the preliminary EDA analysis done on the data. The right hand side shows a chart which shows the overall data distribution. As you can see, there are around 10 conditions, and the prevalence of each conditions are shown here. One of the thing should be noted is a sinus rhythm. Sinus rhythm is a normal heart condition, and other conditions are abnormal conditions of the heart. Okay, and by looking at this data, we see that data is not that well balanced. We see that fewer samples and unequal samples for each classes. So we performed a data augmentation process in the data pre-processing phase in order to balance the data. The second chart is basically a distribution by gender and the type of rhythm. You see that for each gender, there is no difference in pattern exist or observed for both genders. So we don't see any observation or any particular pattern for any specific gender. Uh, Moving on, so this chart represent the distribution by age bucket. So there are four age bucket. We have 0 to 12, 13 to 19, 20 to 15, 50 plus. If you look at this chart, you see that when you compare between the age bucket, there are two conditions stands out for the age bucket 50 plus compared to the other age group bucket, that is 50 plus, and we see the two conditions, that is atrial fibrillation and atrial flutter, are only found in prevalent for the people who are aged over 50. And as you can see here, sinus bradycardia and sinus rhythm sinus bradycardia and sinus tachycardia are highly prevalent in the age group of 50. For the children, if you look at it, sinus tachycardia and sinus bradycardia are the most common arrhythmia conditions. Okay, so this is the atrial and ventricular rate distribution and the box plot. And the distribution chart says that there is a distribution, difference in the distribution. And box plot says that the median of atrial and ventricular rate stands apart, which indicates a strong relationship with respect to the type of the rhythm. And I observed a particular anomaly in the box plot. Um, if you look at it, the highlighted one is the normal sinus rhythm. The This is the atrial rate for the sinus rhythm. This is the atrial rate, ventricular rate for the normal sinus rhythm. If you compare it, this is much smaller. The atrial rate is much smaller in size when you compare it with the box plot size of the ventricular rate. But if you compare it with the other rhythms, um, that doesn't hold true. That for example, if you look at this box, this is much bigger than this box. So that means something is going on with respect to the synchronization between the atrial rate and the ventricular rate. Maybe the ventricular atrial rates are happening more frequently, atrial contractions are happening more frequently, but ventricular contractions are not happening that frequently. Maybe there is something is going on in that side. um, Secondly, the atrial rate is higher in infants and toddlers, which appears to be a normal behavior. um, for example, for the kids, children, and toddlers having a high atrial or ventricular rate, but when they grow up, the rate gradually goes down. So you can represent it as a heartbeat. So it's kind of a normal behavior that for the kids it is much higher, but for when you grow up, it gradually reduces. Moving on, so this is the analysis done for the R-axis, QRS, duration, and QT interval. As you can see, the distribution of R-axis and QRS duration, there is no much difference. And the box plot also doesn't indicate a much strong relation with respect to the type of the rhythm. Um, but for the QT interval, there is a difference in the distribution, as you can see in the chart. And box plot also shows that there is a strong relation with respect to the type of the rhythm. Moving on, these are some of the common ECG signals, just to compare with respect to the normal sinus rhythm. The first one is the normal sinus rhythm, and these are two conditions which are more prevalent in aged people, uh, like atrial fibrillation and atrial flutter. When you compare it, the you can clearly see that abnormality in the ECG signal data when you compare it with the normal sinus rhythm. And sinus tachycardia and sinus brachycardia are commonly prevalent in all age group. You can see that there is something uh, happening, something going on with respect to the ECG signal data when you compare it with the normal sinus rhythm. Okay, now we will look at the methodology and the approach. So here is the data pre-processing step. First, we will load the diagnosis file into a data frame, and we will perform a one-hot encoding on the target variable, and we will balance the dataset by taking equal samples from each category with replace is equal to true. Then we will iterate through the diagnosis dataset and read the respective ECG data and evaluate, and then we will remove any incomplete or corrupt ECG data. Once this is done, we will do a data augmentation. The data augmentation has two steps. The first step is to um, reshape the length by 2500 from 5000 um, by persisting the temporal properties. The second part of the data augmentation is to add Gaussian noise. This is to add a diversity within the data set, because we have taken a sample here with the replace is equal to true. So there is a possibility of duplicate data set within the entire data set. So this is to avoid any redundancy, or to add diversity within the data. And this step is to normalize the data values in the range of 0 to 1, because the machine learning model or the neural network will only accept the data between 0 and 1. So this is to normalize the data values. The final part is to split the data set into training and test data. So we use 80% of data for training, and 20% is for test data. This is just a diagram which shows how the before and after of the data augmentation process. So I have taken two lead data. It's a time series data of AVL and AVF. This is the before original ECG lead before the data augmentation process, and this is after the data augmentation process. So there are two steps we have used, as I mentioned. The first is to reduce the length, that you can see the 10-second window is coming here over here, but if you look at it here, it is actually a compressed version of the original ECG data. So we are not cropping or anything, we just compressing it in such a way that the temporal properties and the structure retains the same. And the second part of the data augmentation is to add slight grain or noise to the signal. This is to add diversity within the data set. And I have used a T-song library for the data augmentation process. Okay, so this is the overall model architecture. As you can see in this diagram, we have input data of size 2500 into 1, which is basically a single ECG lead data coming to the first layer of the model, which is basically the convolutional block. The convolutional block is responsible for capturing any spatial features within the data. How it capture is through something called the filters. So we have the number of filters is 64. The filters are like as a feature detector, and there will be multiple features. For example, the first layer has a 64 filters being applied, and the input data will be convoluted with the filter map by sliding the kernel window, and it will be convoluted. And there is something called pooling, which is basically a way of compressing the convoluted data further. So for example, if you have a pool of size 5, and the result will be derived by taking the max of that from that vector, and the result will be only one value. So that's how the pooling layer works. And we have added 3 layers of convolutional and pooling layer here in this block. And the second block is basically the LSTM, that is the long short-term memory layer. This block is responsible for capturing any temporal features within the data, or any temporal patterns in the data. So this is basically used for the time series kind of data. So we are used to capture any patterns within the ECG data. It acts as a sequence to vector. It's ideal to capture for long-term patterns within the time series data. So finally, this block is the dense layer block, which is basically a fully connected artificial neural network, which will be the final output layer. The output layer has a soft max activation function, and the output will be generated. Okay, so this slide talks about um, a way of improving the precision of certain class. So what I've done is I've created separate model for each data set. When I looked at the performance metrics of some model, even though the overall accuracy was good, um, but the precision of certain classes was low. That's not a good sign. I wanted to improve the precision of certain class. In order to improve this precision, what I have done is I have combined the model result, and a final result is determined by selecting the max predicted from this individual model's result. As you can see, I have used 7 models altogether. Uh, the the first 4 model are using limb lead dataset, and these 3 models are using the chest lead dataset. And it is observed that once we combined this result, and the precision of some of certain classes got improved. We will see the result in the coming slide. We will look at the result. So this is the result based on the diagnostic data set. The model we have used is traditional modeling. I've used SPM with kernel, and the input feature we have used is ECG diagnostic metric or characteristics, what I have explained before. The overall accuracy was coming like 79%, and precision recall F1 score is also 79%. Uh, One of the disadvantage of this classification model is that as you can see, for some of the classes the precision is 0. Uh, this is coming 0. So that we have improved in the convolutional neural network based model. We will look at the result in the next slide. Okay, so this is the result of CNN LSTM based model that uses um, a 12 lead ECG data of dimension 5000 by 1. The overall accuracy, precision, recall, F1 score, everything is coming to 95%. When you compare it with the previous model, the SPM model, it was giving 79%, and this is really a good improvement. And the classification report shows that the precision, recall, F1 score for all the classes is looking good, and the confusion matrix, all the numbers are lined up to the diagonal, which is also looking good. Okay, so the next one is the challenges and the improvement. So one of the challenge I was facing was, um, I did lot of time in running the trial runs to find out the right combination of the parameters. We used some parameters such as epoch, number of kernels, number of filters, kernel size, etc. So finding the right number for these parameters is really crucial uh, to find the better model. So one of the improvement we can use is it's to use the hyperparameter tuning. So it's kind of a framework which where you can define the list of um, possible values for all these parameters, and the framework will automatically select the right parameters for the model and the data. With that, we don't have to spend much time to fine tune the model hyperparameters. The second improvement I was thinking is introducing an ensembled model architecture. So this is again a different way of improving the precision of certain classes. It's basically a sophisticated way of combining different models. Uh, yeah, these are the improvements. Yeah, thank you for listening for this presentation. Thank you.